Ah, Walaikum assalam. Okay. Previously, we were looking at this logistic regression. Actually, logistic regression starts from here. This was the input and this was the output. I'm going speedily and quickly just to take a review of those previous things. Then we started with this equation that how the inputs and their weights are multiplied, and then we are summing them up and we are adding bias into it. And then we have something z here. That z we are passing into this sigmoid function, and this will give, so these are the values for the z, and then it will give us some probability value from this 0 to 1. So then what it will give us the uh, probability value for this class y, which is available in our data set. And then here we are confirming that this is the probability value. So we are using these two equations. If the class is predicted, then this is the probability. If the class is not predicted, then this is the probability. And then we are summing them up. And if the sum is 1, then we are confirming that it is the probability value 1. And for decision, whatever the probability value we have, if we have a threshold zero point 0.5, if the value if this value is higher than that 0.5, we can say class 1 is predicted. And if it is less than, then we can say second class is predicted something. And when this class predicted, then we are calling this y a y cap, because now this class is predicted by the model. Okay, by the model. Actually, it was predicted here, but here we are finalizing. Anyhow, then we have seen this example of sentiment classification through this logistic regression. We have taken three features from this data. This was the sample to us. We calculated these features from x1 to x3, and then we have taken a vector of weights and a value for the bias, and then using using this equation, we processed this thing with the first class, and this is the vector of the weights, and these are the values, or you can say feature vector values for the inputs. This is a vector of the input, and then we multiplied first value with first, second with the second, and then we summed it up, and finally we added this value 1.1 into it. And then we got this one after applying the sigmoid function over it. You can use the Google actually, and that will give you 0.7. And then subtracting this 0.7 from this one, we are getting the probability for the other class. And if we have that threshold, which is 0.5, then we can say here the value is greater than 0.5. So then this example is the example of a positive class, okay? Because here the other class has lower probability. So then final decision is this paragraph, these comments are these review comments are as a positive class. This is our decision for that example. Now, to our loss function. There was a slide. Here we talked about that every probabilistic machine learning model or classifier, actually, this classifier will have four components. Four components. The two components we discussed in the previous lecture, and two are remaining. One is objective function. It is remaining because we have to design some formula to calculate the error. Okay, we have to design some formula, and that formula, for example, here in logistic regression, it would be cross entropy loss function. This is the name of that formula, and this formula will calculate the error. And our objective, and then this is one, and the other is algorithm. So when you have that error, then Okay, you want to minimize the error here. Your objective is to minimize this error. Error mean loss, loss in your accuracy of your model. Okay, you can say. Okay, you can say error is what? Error is a loss in accuracy of your model, and we want to minimize our error so that our accuracy will improve. So this is one thing that is we have to build some formula to minimize this error. And then the other thing is algorithm. We need that because in these models the weights will be used, and weights will be continuously we are using with the input variables. Then what those weights are basically causing this error or whatever. And then what we through this algorithm we want to optimize our objective function. Basically this minimization you will do this here in this algorithm when you will do this iteratively. So these two parts are concerned are related to the training phase of your model, to the training phase of your model. So now we are moving towards that first with the loss function. First with the loss function. And now we will try to understand this loss function mathematically. Okay, we will try to understand. If you will understand, this is the way to write your thesis finally at the end of this degree. I told you already, okay? You have to explain your model. And how you can explain your model? You can explain your model mathematically in your thesis. You don't have to present source code there. Nobody will see your source code. People will only see your algorithms, your mathematical equations, and the discussion about them. So let's see it. So this is the third component, loss function of the, we are going to see the loss function of logistic regression. But the question is, our model is using some parameters. And those parameters are what? The weights and the bias. And then we have the input, which is x1, x2, x3. Huh? We already talked in the previous lecture. Xi's are the input, but then we have the weights, W's, and this B, bias. How our model, the question is how our model will learn something about these two things. We have a first point here, and then we have a second point here. First point is saying that we can learn these weights by calculating the distance between the class which would be predicted by the model and between the class which would be available in the data set. Available in the data set. For example, if you will remember the PIMA Indian diabetes data set, if you will remember, then what were the columns there? Pregnancy, pressure maybe, uh, something paddy, something skin, and something like that, 8, 9. And the last column was class. And the last column was class in that database. Sorry for I'm using mouse, okay? So the last column was class. And the values in that column were 0 and 1. 0 means one class, 1 means other class, opposite of that, huh? Opposite of that. Now, the first thing, if we want to learn the weights, if our model wants to learn the weights, then you should have to take care of 2 points. The first thing is you have to calculate the difference between the output of your model. This y cap means the class which is predicted by your model. And this y means the class which is available in the data set. Okay. This 0, 1 which are available in this column for this whole row. We are saying if you have these things, then this is class 0. And if you have these things, then this is class 1. And you are going on like that. So the class decision which is available here in the data set, that is called y in our calculation, which we have started from the previous lecture. And y cap is called the class which would be predicted by the model. Which would be predicted. So then what? We have to calculate the distance between the two decisions. One decision is available in our data set, which we are calling gold output, okay? Gold standard, you can say. And the other class is predicted by the model. So we have to calculate the distance between them. And when you will calculate, this is called loss function, or the other name is cost function. And in logistic regression and neural network, we are calling it cross entropy loss function. Second thing. So we have to calculate this distance. For what? If we want to learn these weights. If we want to learn these weights, if our model wants, when I say if we want to learn, it means model, okay? Not we, okay? But English is not our language, so sometime we will say something like that. So we can only say something correctly in our own language, okay? So, but here we are using the second language or third language, you can say. So that's why it can happen something like that. So the second thing that we have to take care that, okay, we will calculate the distance, but then we need an optimization algorithm. The algorithm which will optimize the values of these weights, okay? And one algorithm is gradient descent or the stochastic gradient descent. Gradient descent, simple version, stochastic gradient is a minor updated. You can use gradient descent in linear regression, and stochastic gradient descent in logistic regression. So you will use this algorithm and it will do what? It will iteratively execute something, and then it will optimize the weights of these, the values of the weights and the biasness. And I will use the singleton. It will optimize the weights, and that weights mean W's and also the B in it. And this will do what? And then finally it will minimize the loss function. It will minimize the error, you can say. Okay, moving next. This is the background that we made, huh? Now we will start with the first thing. What is first thing? First thing is calculate the distance between the y cap and the y. Then theoretically in sentence form, how we can write? We can write that we have to calculate the loss, L for loss, between the class y cap and the y. What it means? It means how much is the difference between y cap and the y. True y means the class which is existed in the data set. So this was the question that we introduced here, huh? And we started with this first point. We started with this first point. We have written this thing in a sentence. Previously, from our previous lecture, we know that y cap is what? Y cap is sigmoid of w dot b plus b. If I will go back just to show you, okay, somewhere. So here you can see this y is sigmoid over, or maybe here this is the z, and then here we are calling it sigmoid of z. Z is what? W dot x plus b. W dot x plus b. And then finally we are reaching here, and then finally we are predicting y cap. This y cap is basically y, but if the model has predicted, then we are calling it y cap. Anyhow, y cap is basically what? Sigmoid of w dot x plus b. This is from the previous discussion. Anyhow, so we are writing our first point. How we can calculate the distance between y cap and y? We are writing it theoretically in a sentence form. First, we can say that this is lost. We want to calculate the loss between the y cap and the y. In other words, we want to calculate the difference between the y cap and the y. So the first point, we have written down this first point here theoretically. Now we are going to make this theoretical sentence into the form of an equation. So here we have to find the difference between y cap and y. What this means actually? It means that we want that this class, which is y, which is available in our data set, We want that this class Y would be predicted by our model most likely, most of the time. We want, this is the meaning of that. We want that this thing which is available, this decision, for example, one row and its decision is available in the model, in the data set. And I want that this class Y would be predicted by my model most likely, most of the time. Most, when I say most likely, it means probabilistically. Huh? So it means that I have to use some probabilistic equation here. It means that I have to use some probabilistic equation here. I will give, and what you will give? You will give the input and then it will predict. So then if you will have to use probabilistic equation, you will give something and then it will predict. It means you have to use conditional probability. Conditional means you have to give something and then you will get your probability. So that's why we have to use conditional maximum likelihood estimation. This is the title for that conditional probability, okay? The complete title. So one thing that you have to use, this thing, conditional maximum likelihood estimation. Through this, you will maximize the probability of something. And the equation for that is probability of y given x, huh? Probability of y given x. This is the equation for this thing. And the other thing is, in the data set, my class Y has what values? Either 0 or opposite. Either 0 or opposite. Either 1 or opposite. Only two values, 0 and 1. When you are going to predict some class which has only two possibilities, 0 and 1, it means Bernoulli distribution. Okay? It means Bernoulli distribution. So you have to use Bernoulli distribution. You have to use the equation of Bernoulli distribution. I can show you the equation, for example, if I will uh, maybe, come on, go somewhere else. I want to. Look at here. FKP, P raised power K plus 1 minus P, and then its power is 1 minus K, something like that. This is the equation. This is one equation. And now look over here. Y cap power Y, 1 minus Y power 1 minus Y. Similar equation, okay? This is the equation for the Bernoulli distribution, which means your data in your data set is distributed like this, like 0 and 1. So that's why you have to use Bernoulli distribution. That is Bernoulli distribution. And you have to use that equation for finding the probability. So that's why we are writing, we are going to find the probability, conditional maximum likelihood, probability of y given x, x would be input and the class y would be predicted. We want, the probability of y class would be calculated, and we are using Bernoulli distribution, which is like that. Y cap has the power y, and then one y cap is what? The class which would be predicted by your model. And the y is what? The class which is available in the data. And then y, and then you can understand this, the rest of the equation. 1 minus y cap, 1 minus y, it is written according to Bernoulli distribution. So if you are writing thesis, you have to give your references. I am writing this by using this reference. I'm writing this by using this reference. You cannot go on air, huh? So, so now, if the class y which is available in your data, if that would be predicted, put the value of y is equal to 1 in this equation, and then you will get what? You will get your probability of y given x, y cap, from this equation, okay? And if the class which is available in your data, if that is not predicted, 0 means that is not predicted. Actually, it means predicted, it means not predicted. The opposite side. Then put this value here in this equation and you will get this thing from this equation, 5.8. So now, continuing our discussion further. We are moving towards, we have to calculate what? We have to calculate, we have to build a formula for calculating the loss, for finding the error and then minimizing the error. But we have started. Okay, moving next. Here we are not using weights. Here we are using simply the input and using the class label. If, for example, we are using what? When we are calculating this probability of y given x, actually, if you will remember the previous discussion lecture in the previous lecture, we were multiplying x with the weight. We were multiplying x with the weight. When we were calculating this probability, we were multiplying x with the weight. Here you can see I am multiplying x with the weight. So now when we will calculate this probability, then we will use these weights and it will maximize. And then I will use these weights to maximize the probability. Or you can say I will use these weights to calculate the probability. Leave these words maximize or whatever. If you are going to calculate the probability, sometimes these values would be high, can be high, sometimes positively high, sometimes maybe it is a probability. So that would be, it will be after the decimal point, you will have a lengthy series of digits. After that, because it is a value, maybe you will have 0.99999 and a lengthy series. And this lengthy series is a complication for the machine. Huh? Maybe you have heard this. If you are a student of computer science, then maybe you have heard this. Because if it is too much lengthy, machines normally don't handle this thing in a perfect way. So that's why. So we want to keep our calculation simple. And then what? If you want to keep your calculation simple, then you have to take the log on both sides of that previous equation. This equation, this equation. You have to take log on both sides. And okay, then we are taking log. Log probability of y given x is equal to log and the same equation. And the same equation which were here. By applying the log on equation 5.8, we have now this equation. And if you will apply this log, it is log mn. So then it will become n log m. By using that log formula, log m raised power n, it will become what? N log m, because it has the power. And then similarly here, it will become what? 1 minus y log and this way. And then you will have a new equation 5.9. So now we reached at this step. Now we will give further reasons and we will move to the next step. So this equation 5, through which we will get the probability, this P is for the probability. So we will get the likelihood or the probability from this equation. This equation is what? This is conditional maximum likelihood estimation, complete name. Short is what? Probability value. So if somebody will say that this is likelihood, okay, that is okay. If somebody will say probability value, that is also okay. So here we have some value for the likelihood here. That would be through this formula. When we will run this, we will get the maximized value for this class given this input. Or you can say, if this formula we are going to build for the loss, then we can say it would be, loss would be maximized. Loss function would be maximized. Loss would be maximized. Then the question is, okay, if you will get some value for the loss, maybe something 0.45 or point something, how so you have to subtract this. Maybe you cannot add this loss into your final result. Huh? You have to subtract this from something. This question is coming into our mind. Or on this step, what is the other thing that you can do easily? You can flip the sign. You can flip the symbol. If it is positive, make it negative. Because it will be, when you will use it in algorithm, that algorithm will iteratively calculate different values, and then you don't have the time to do anything. And but when you will flip it sign, it will be automatically considered. So then what? So we want to minimize this loss. So here the loss is what? In this equation, the loss is maximized, positive value maximized. And in our model, we want to minimize this loss. We want to minimize this loss so that our accuracy of our model will increase. You can also understand through this sentence. And then what we will do? We have to flip the symbol. And then what? We have to, if it, and then here we are calling it, and here now we are giving it a new label. We are calling it loss from y cap to y. This is the thing that we started, okay? Because now our full formula is almost in the final shape. So that's why we are coming back to our own terms. We are now giving it this formula that we have. We are now saying that this is the formula for the loss. And loss from what? Loss between the predicted class and the class available in the dataset. And we are calling it cross entropy loss because we are in the logistic regression. Okay, and then we are giving putting minus sign here on the left hand side and also minus sign here on the right hand side of equation 5.9, and we are getting equation 5.10 simply. And we are getting equation 5.10. I'm not explaining. I'm using 5.9, so it means we already discussed something there. So it would be easy for me to just quote that equation that I'm using equation 5.9. Moving next. Now in this equation, we are not disturbing this equation too much, but we are introducing the weights in it. For example, what is the equation for y cap? We already know that it is sigmoid w dot x plus b, which means sigmoid of z. Oh, from the previous lecture. You will give z into it, huh? And then sigmoid of z, you will get the answer for y cap. First y, then when you will have the threshold, by using that threshold, you will get y cap, huh? Anyhow, so now we are replacing the y cap here in this equation with that sigmoid w dot x plus b. And then what? Here we have y and here we have y cap. So now replace this y cap with what? Sigmoid w dot x plus b. And here we are replacing. And here we are replacing. So this is in place of y cap. And this is also in place of y cap in this equation. So replace this y cap where you have with what? With sigmoid w dot x plus b. And when you are replacing, you are getting this one. So now you have this equation with weights, because we started our story. How we will learn these weights? We started our story. How we will learn these weights? So we started equation and finally we have our equation into the form of weights. But this equation is not something final. So we are calling, now we are also calling this a loss for weights. We will calculate the loss with respect to weights. W is weight, B is biasness, and C, cross entropy. Because we used this term here in the previous step, so that's why we are continuing that term again here with the weights. We removed the y cap here. We removed the term of y cap from here. So that's why now we have this equation into the form of weights. Okay, now I have this equation, but this equation is only for one input, x. This is not for all inputs, okay? This equation that we started from the beginning, this equation is only for one instance, okay? For one input. We have to convert this equation for the whole data set. That step is remaining. But before that, let's confirm that this equation that we have here for learning the weights is okay or not. We have to confirm. And here in this point, we are saying that this equation is okay. Why? Because we are using log. And then we are calculating some sigmoid is giving us some probability value. Huh? Sigmoid is giving us what? Some probability value. And we are taking log. And normally, if you have 1 and if you are taking log of 1, so negative log of 1 is always what? 0. Because we have negative here. Huh? We flipped the sign in the previous step. And now we have negative log of some probability value. Huh? This is the meaning of this equation, this whole equation. So then what? If you will negative log of 1, so maximum value of probability is 1. So if you will take negative log of 1, you will get 0. 1 means class is predicted properly. What is the meaning of these words? 1 means class is predicted properly, no loss. Okay, this is the meaning. If I will ask you these questions, huh? If I will ask you these questions, will you be able to answer me the questions like that? What is the meaning of this? What is the meaning of this? Huh? Anyhow, you can start reading your news, okay? And after 30 minutes, I will ask you what is the meaning of this. Huh? What is your good name? Salam? Muhammad? Abdus Salam. Okay. So Abdus Salam. Negative log of 1 is 0. And the negative log of 0 is what? Infinite loss. Which means if the class is not predicted, if the class is not predicted, then you have the loss there. And it will give you some value for that loss, infinite loss. If you will take the log mathematically, I have highlighted it in blue. If you will take log of 0, log of 1, you will get 0. And similarly, something like that. This is what we want. This is what we want from our model. So that's why this equation, whatever this negative log of this probability, this equation is what? Negative log of this probability. So then this equation is convenient. It's suitable. It's okay for our model. And then it will this equation will do what? It will maximize the probability of the correct answer. And when the correct probability of probability of some class is maximized, the probability for the other class would be automatically minimized. This is what written here. Now moving next. One point is remaining. This example is only for one input. We have to convert it for the whole training data set. We have to convert it for the whole training data set. And here we are converting. And here we are converting. I have copied some equations here so that I will not go back to those slides. Equation 5.10 and this equation, we will use it somewhere in the next calculation. But if we will have the whole training set, then it means we will not have only one example X. Then we will have Xi. So now we are assuming Xi for the inputs. And then Yi means the class decision which is available in the data set. I explained you in Indian data set, one column value, another. So you have this one row, and then the last column is class. It will have the value maybe 0. This is the decision of that class. And similarly, you have these rows, which is going, and here you have the decisions in the data set. So this is called YIs. So one value y1, y2, y3, y3, y4, yi's. And this is called, okay, you can call it x1, x2, x3 into the form of vector and so on. So xi is what? The training features are the inputs, ith inputs. And this y is what? I told you that this is the class label which is available in the data set. In the data set. Now, I will previously, whatever my previous equation is, it is something like that, log of probability p y given x, and this equation on then this equation. So I am using that information, mixed information. So if I want to calculate the probability of for the whole training labels, training labels mean y's, all y's, y given x, y1 given x1, y2 given x2, y3 given x3, y4 given x4, and so on. So if I will say yi's, if I will write, then mathematically it would be something like that. Given xi's, this would be like that. So training labels, I use the word label. Label is here. Training labels, training labels for the y variable, not for the x. We want to calculate the probability for the y's which are available in the whole data set, and the log from the previous equation. From the previous equation, we have the log here. We have actually minus log here. We will use that minus. Okay. Okay. So log p. So that is the same. Then here, for the whole data set, I have to calculate probability of y1 given x1. And then I will multiply this probability with the y2 given x2. This pi is from I to m, which means m examples are there in the training set. And what is the meaning? Y1 x1. When I is equal to 1, then y1 given x1. You will calculate the probability for that using this equation, using this equation, or even the final equation. And then you will multiply that probability with I2, pi I y2 x2. Whatever the result, you will multiply it with probability of y3 given x3. And in this way, you will go on up to the point of m. And finally, after multiplying all those probability, you will take the log. So that is the same equation. The previous equation is basically, this is only for one input, and this, and here we are representing it with LWB. LWB is what? LWB is log PYX. That is for one input, and here we are saying it, this is basically that thing, but PY given X for all i's, one time, third, 2, 3, 4, and then you are multiplying all those values and taking the log. So that is basically the same equation. So basically it is what? It is the same equation. I can erase it. So it is basically the same equation. We are using this equation. I have this new name for it, but keep it aside. But actually its name is what? Log PYX. And this is only for one input X. And that is what? That is for all. And then you have to do what? You have to calculate it for y1 x1. You will have the probability. Then you will have to calculate it for y2 x2. Then you have another probability, multiply. Then you have for y3 and x3, and you have to multiply all. That's why you have the pi. And if we have some formula, something like that, where you have the log and things are multiplying, like there, log mn, then this is the formula. You can open it up. This is the log m plus m. And here you are converting this product into the form of summation then using this formula. So now this product is converted into sigma. Summation I is equal to 1 to m and log pi yi given xi. You are separating by using this formula of log. Clear? Clear or not? This is the simple formula, but it is in a complicated, in a collective form, okay? In a aggregative form. So that's why. Otherwise, if you will open up, then this is something, one thing is multiplied with the other thing, and then you are just separating. Nothing else. By using this formula. Okay. Now, this log pyx, forget this I, and then you will have your formula, this formula back. Log pyx, huh? Then you have this formula back actually. Only for understanding. Only for understanding. But this formula is only for one instance. And this is for the whole training. And here in this formula, we are also labeling it cross entropy loss, y cap and y. And similarly, we are again going to use the same term again, cross entropy loss. And this is now y cap I. Y cap would be the class predicted by your model. And this yi would be the class decision which would be available in the data set. In the data set. And then other sigma is same, and you are also introducing minus, which was there, okay, which was there finally. So we have now this equation 514 finally. But this is what? This, you have calculated all the loss for all the inputs. You are calculating all the loss for all the inputs. And loss between y cap and y is calculated through that previous equation. But you are summing them up. Due to this summation, you are summing them up. And if you are summing them up, you will have finally a great large value, which is not a true picture of your value, huh? Then what? You have to take the average. You have to finally take the average. You have to take finally the average. So that's why we are going to take the average. Then we are repeating the same thing again. This same thing repeating. I can clear these red. So I am taking this same thing again here, and then I am dividing it with m. M is the total number of examples, inputs, huh? Okay, now here in the next, we are opening it again, nothing else. We are converting it into the form of weights, nothing else. So this is our equation finally. This is our final equation, final summarized form of our equation for the whole training set. Now we can, and this cross entropy loss y cap I is given here, huh? Is given here. You can use this, and then you can replace this y cap with w dot x simply, or you can go back directly to this equation, huh? You can go back directly to this equation 5.11, which is y log w dot x plus b. Let's see then. Here we are writing, okay, we are introducing minus sign back again, 1 over m, and then here yi. Wherever you have y, make it yi, and where log, and where you have the y cap, replace it with sigmoid w dot x plus b. And x is what? Xi, because we already said we are saying multiple inputs xi, and multiple class decisions are also available in the data set, which is yi. So we are converting. So by using this equation 5.11, we are converting this thing, law cross entropy loss of y cap y is what? First it is this, and then it is this, huh? So we are converting our equation, this summarized form, into opened form, and then we are saying it 5.11, 5.15. We are calling it 5.15. This is the equation. Now, this is your equation for the last function. This is the equation. Actually, it is not calculating anything. This is the equation. Your algorithm will calculate. Okay. Now you will build an algorithm. In that algorithm, you will fit this equation there. And then in the iteration, this equation will work, and then you will have the values. This is the equation that you have designed for the calculation. So that is what you want. to minimize the error, to minimize the cost, to minimize the loss. But how we can minimize, how we can find the final value? If we will have the algorithm, then we will fit this equation into that algorithm. That's why we are moving towards this gradient descent in the next step, okay? So can we take the break now and then I will start this gradient descent? Or I can start a little bit. What I have to do? Is it the prayer time or not? It's in 2 minutes. Okay. Then we will start a little bit, huh? And then we will stop at 6:30. Hmm? So now algorithm is needed so that we can fit this equation in that algorithm, and then that algorithm will do some iteration again and again, and then these weights will be optimized. This equation is okay. This will calculate something because weights are there. This will calculate something. First it will do something for x1, then it will do something for x2, then it will do something for x3, x4, and so on up to xm, because we have m inputs, huh? And similarly we have the m weights. Biasness is fixed, bias is fixed value. So this will do that, but we have to fix this in some kind of algorithm. So that's why now we have the gradient descent algorithm here. That will do what? We want to use this algorithm to find the optimal weights. And what is that optimality means? Minimize the loss function. Minimize the loss function. So now if we want to use the gradient, then we are making a little different representation. We are going to change our notation. First, we were representing W's and B's exactly as it is in the equation. In the previous equation, you were saying W's and B's as it is. But now we will represent these W's and B's with the symbol theta. With the symbol theta. We are going to make some equation again. And in that equation, we are using theta, okay? And theta will represent what? It will represent weights. Yeah. I am calling simply it weights because bias is also a weight, so weights. Okay. So weights mean W's and B, nothing else. So if I will use this theta, then my previous equation that you will have here, this short form, this equation, huh? Then it will be, it is what? 1 over m sigma and then L and then y cap yi. Or you can take this one, 1 over sigma, 1 over m sigma y, and the here w's and b's will become theta, you can say. And here I'm saying 1 over m sigma I to m, and that loss, and then yi the class which is available in the data set, xi is the input, and w's and b's I am representing with this theta. Okay, this is a new representation for your previous previous equation. Okay, all your wb's is in this theta. And what I want to get the minimum of this theta. When you write argument of minimum, this is the meaning of the meaning of this is you want to get the minimum of this variable theta. And when you will get that minimum, that would be given to you by your model, and we are calling it theta cap. It will be calculated by your model. It will be calculated by your model, that theta cap. Theta cap would be the value that would be given to us by our model. This is generally described here. This is visual explanation, okay? Visual explanation, which I was saying that have you studied something visually or mathematically? So this is visual, okay? So if you have this is the cost and this is the weights, and if you have some point here on this curve, this is your initial weight, initial point. Then you will do what? You will draw a straight line here. This straight line is called gradient. The other name for the gradient is derivative. The other name for derivative is the gradient, derivative, and the other name is slope. Okay. So these are the three same names. Okay. Three same meanings you can say. So we will draw this gradient and we will see the value what it is. And then in the next step, we will do an increment and then we will move to the next step here. And then we will draw the line again. We will calculate the gradient. And then we will see what is the rate of change between the values. Huh? What is the change? And then we will move this point next. Suppose at this point your cost is high, huh? Your cost is high, then you have to move down, okay, to lower the cost. So then this way you have to select the next point and then you have to draw the gradient. You have to select the next point, then you have to calculate the gradient, and then you have to go to the next point, you have to calculate the gradient, and finally you will be at the global minimum. Hmm? You know what is global minimum means, huh? If you have studied AI or something, then you know, huh? So then you will reach at the global minimum, and global minimum is the deepest point in your state space. And if it is the deepest point, this would be the last final calculated value. That would be the minimum value, okay? Then here you will have the cost minimum if you will calculate it through gradient. Okay, so now that whole story is written here. You can read by yourself, and I am moving forward. So, gradient is one name, derivative is another name, slope is another name. Okay, you can write it here. Okay, and why we use these gradients and derivatives? We normally use this gradient and derivative to find the rate of change in some quantity or in some function. For example, here we want to find the rate of change between the quantities, and quantities is cost. We can also use gradient and derivatives to find the approximate value or approximated value for something. We can also use this gradient and derivative to find the tangent of a curve or something normal to a curve. And another use is we can also use the gradient and derivative to find the minimum and maximum value of some equation. Expression mean equation. So you can also use gradient and derivative to find the maximum or minimum of some equation. And here we want to find the minimum of some equation, huh? And here we want to find the minimum of some equation. We have the equation. Now the new form of the equation is this, which we derived from that previous equation, huh? And we want to find the minimum of that. So this is our starting for the gradient. This will again have the calculation, huh? This will again have the calculation. We will go through this calculation anyhow. We want to find the minimum. So that's why we will use this gradient, gradient descent algorithm. This is the reason you can give why we are using gradient descent, huh? Because we want to find the minimum of loss, minimum loss. Okay. So this is gradient. Gradient can be used for these things. And then question is, what is the derivative of our cost function? This is our cost function. This is our cost function. This is our cost, the loss function. Huh? The other name is cost function. And the question is, what is the derivative of our cost function? We want to minimize it. So that's why minimum of that cost function is our gradient. The minimum of that formula equation is our gradient, our derivative, whatever you want to say. And in mathematics, you know how to represent derivatives. For example, something is written here, d by dw. What did it mean? It is a derivative of w with respect to w. You know this from mathematics. from mathematics. This is the representation for the derivatives. So then how we can find this minimum of our cost function? Our cost function from our previous equation is, it is based on weights. Huh? Weights are there. So if weights are there, how we can do that? We can optimize these weights by subtracting this value. By subtracting this value, this is what function, this is a function which is taking input x and okay, it is mapping input x and mapping between the input and the weight. This f of x w, normally if it is a function you can say okay, it maps between the input x and the weight. For example, x1, then it will give you w1. If x2, then you have its respective weight w2 or something like that. So it will do what? How we can minimize that previous equation, which is the equation for the cost function? We can optimize by subtracting. First we will calculate the derivative. First we will calculate the gradient. If I will use the word gradient, derivative, slope, same meaning. So first we will calculate the derivative for those weights. First we will calculate the derivative for those weights. And then we will multiply them with the learning rate eta. And then we will subtract that. We will subtract that. Then we will subtract that thing from the current weight. So this is what you have to do to minimize that cost function. What it means? So how I will get the optimized value for my weight? Okay, I have some weight, you will have some weight, okay? You will do what? You will take the derivative of that weight. You will multiply that weight with eta. That weight that you will have, that will have some values. That is the same values here, okay? That is the same. You will, whatever values you will get here, then you will subtract those values from here. And then you will have some updated value. Those values you will again update with the weights that you already have. Don't be confused with this t plus 1 and t and something like that. The meaning of it is this: initially you have the weight 0, okay? You will take the weight 0. Whatever your weights is, if w1 is 0, biasness is also 0, learning rate cannot be 0. It can be something 0.1 or 0.2 something. You will take the derivative of your weight, either it is 0 or what, you will take the derivative. There is some steps to take that derivative. We will see that. And then you will multiply it with the learning rate. Then you will have the new values, not 0, okay? You will subtract these new values from these zeros because you have these weights 0. And when you will subtract, you will have the new values. But I'm sure that it would not be 0. And then you will update those values again in the weights that previously you have the 0 values. Now your weights are updated. Now your weights are updated. This is what this equation is saying. This is what this equation is saying. So initially you will have some weights. You will have to take those weights and then you have to take the derivative, multiply with the eta, subtract it from the same weights, and then update the value in the same weights. And here WT plus 1 means you are getting the new weights for those previous weights in time t plus 1. Now the time is t plus 1, okay? Now the time is t plus 1. Anyhow, moving next. Oh, 6:30 is okay, so I will start from here, inshallah, after the break. Hmm? Yeah, you can turn off. So we were here, we saw something here, how First, what is the derivative of our cost function? The derivative, the gradient is that we want to minimize our loss or cost function. And then how we can calculate or how we can optimize actually. Calculate was the previous step, optimize. How we can optimize, we can take the gradient first, and then we will multiply this gradient with uh, learning rate eta, and then we will subtract it, and after the subtraction we will update the values on the right hand side. This is the equation that we formed, but this equation is now for the one input x and the single weight, you can say. Now we have to move our equation for all the weights, for all the weights, not only for w1. Okay, so for w2, w3, up to wm. So what, now we have to extend our equation, our function, from one scalar variable w to many variables. So how we can do that? So we normally we are calling that this is our gradient or this is our derivative, our derivative. If gradient or derivative have further divisions, then you normally call it partial derivative. Okay, you have a bigger concept that is called derivative, and then you have a smaller concept that is called, the further division of that derivative is partial derivative. That's why its name is partial, and all those partial derivatives then combine with each other, and then they will form finally the form of the bigger derivative. So derivative and gradient is same thing. Slope is also same thing. Now this equation 5.17 is a equation for finding the weight including derivative for one variable, you can say, or for one weight. We want to extend this equation for all the variables, for all the weights. And then it means, okay, if we want to do that, then finally I will say that this is my gradient, and then that gradient will have the other name is, this is my derivative, and that derivative will have partial derivatives in it. So now for all the variables, I will say finally that is my final derivative. Okay. For all variables, the final derivative, I will call it the derivative or the gradient. But the variables which are in it, W1, W2, W3, W4, I will calculate their derivatives as partial derivative. Okay. Now I am going, because I have to consider all variables. So now I have to build some vector to represent all those things. So now I'm going to represent my gradient or my slope, and I will use this symbol for that in the equation. That is inverted triangle, you can say, So I will use this, and for partial derivative, this is the notation available in mathematics, partial over partial w. How we read that? Partial over partial w. This is the derivative, but is the partial part. It is the component of that bigger derivative, you can say. So now, if you will see, this is the equation for all the variables. For all the variables. Here, this symbol means gradient or the bigger derivative, or the derivative. I can say it simply derivative or the gradient. And gradient theta. Theta means weights, W and B's, And if it is gradient, it means it will consider all the weights. It will consider, this is the left hand side. The opened form of this left hand side is this right hand side. It will explain. And all this, and this right hand side is containing what? Partial derivatives. Partial over partial W1, first weight. Partial over partial W2, second weight. Partial of partial W3, third weight. And so on. Partial of over partial Wn, the last weight. And then this is our last function. This is the same. This f of x comma theta means y cap. This means y cap. Okay. This f of x theta means what? Y cap. The previous term. The previous term, this term from where we started our story, loss of y cap. What is the difference between y cap and y? So that is, so this f of x comma theta is y cap. What is the difference between y cap and y? This is that equation. That equation we already finalized in the previous slide on the previous topic. Okay, what is the final equation of the last? So we have finalized this equation already in the previous step, but we have to calculate this loss, and that loss was, we have calculated that loss for one input and also for all the inputs xi's and yi's. And this loss it is only for, it is written here, x is one observation, huh? X is one observation, and then this theta is representing weights, w and b's, and here we are dealing only with weights with one observation, but weights would be w1 w2. We will change these weights and we will get the minimum one. So here theta, so this loss is, this equation is representing the previous thing. This equation is representing the previous equation that you got in the previous slide, that was for loss, which is L y cap y. That is something like that. But this gradient is derivative, or I am using another word, bigger derivative, for understanding. For understanding, or I can use the word gradient theta. It will have partial derivatives in it. And how we can represent it? Like that on the right hand side. This is the partial derivative of the same loss. This is the partial derivative of that same loss. This is the partial derivative of that same loss equation that you have. And in this way, we have this new equation 5.18 from this. We started from this with the weight of, with one input observation, and we reached here. So this equation is representing the loss or the gradient. The gradient, we want to do what? We want to minimize the loss. How we can do that? By calculating the derivative. By calculating the derivative. This previous equation was, the derivative was only for one weight. We want to convert that equation into for multiple variables, for all the variables, for all the weights that we have here in our model. And here is that equation. This equation is for all the weights. For all the weights from W1 to Wn. Now, okay, if this is the equation for all the variables, now then this equation will have another form, because this is only for one variable, for one weight. And now this, by using this concept, now this equation will be updated. And now you have theta t plus 1, theta value of theta at time t plus 1, value of theta at time t, and then this delta L f of x comma theta, this one, this equation, that is now becoming the part of this equation 9.19. This equation is now becoming the part. This 5.18 is now becoming the part here. Why we have reached on this? By using this concept of equation 5.17. This is only for one weight. This is only for one weight. And this is representing for all weights. In this way, you can calculate the weights actually. This is the equation which will give you finally the optimized result for theta, for weights. Theta is what? We have assumed initially, theta is what? Weights, W and B's. So this is the equation that will give you finally the result. Okay, from this point, now we are moving forward. Yes.
So here the partial weights you're talking about, the number of weights are which is represented by n. It's reflecting the number of features, right? Each feature has a weight. So you're taking the
each feature mean each input, huh? Each feature mean each each, for example, you are saying that x1 has that all these things.
Yes. So one row has 5 6 features like the pressure and the skin and the age. And whatever. So each feature has its own weight, right? We are taking the differentiation for each of these features.
This x is one input. You can say it is x1. And this is only the weights. Because if you have n features or f in n inputs, then you will have n weights. And now you are trying all these. This equation is you are trying only on the weights. You are checking all the weights on this input x1, and then you will check all the weights on then x2, and then you will check feature. Yeah, on the second feature. And in this way you will go on, and in this way you will go. So here our observation is single, but our weights are all. Yeah, all. We are checking the whole vector of the weights. We are checking the whole vector of the weights. Anyhow, any other? Hmm? So this is the equation we reached. Are you angry? You're looking like that. It seems that something is wrong with you. Huh? Anyhow, I will not give you these mathematical equations in exam, okay? I will give you examples, okay? Now be happy. This is only for me, huh? So now we are on this equation. These equations actually give you the pure understanding of that model. But now machine learning students normally they don't want to get into the depth of these models, okay? They only want to use that. This is what the definition of machine learning is, okay? You normally learn how to use that thing, okay? You don't want to know what is that thing, huh? But being a but
function on
yeah, but being a student of computer science, you must have to know what that model is actually. At least once in a life, you must have to know what that model is, because you have to write your thesis. You cannot write your thesis without explaining your model like that. Okay. Anyhow, so we have reached on this equation 5.19. Now, so now we know what is theta. Theta is what? The W's and the B's. And now in that equation, if we know from that, we now going to update those values in that small equation. In that small equation, especially this one, this equation, gradient L f of x semicolon theta comma y. So you can say this y is also the same class which is available in your data set on one row, okay? And this is also x is the data of one row. And this theta, this can vary. This can be varied through your algorithm, which we are going to discuss next. It can be changed, and then you will see what the final minimized value you will get. Anyhow, so we are going to say something now on this part now. This is the loss function. This is what we are taking the gradient, but this is what L means, loss function, that we already calculated. We are presenting that equation here again. We already have taken uh, this equation y logs sigmoid of w dot x plus b. We have already taken this equation somewhere. Hmm. This is the average, huh? But this is what I want, or this one, huh? Or this one, 5.11. So now we are going to use these equations. So we want to do what? We want to update the theta. And for this, what you have to do, we have to focus on this part, which is gradient of L. And this f of x theta is what? Y cap. It is what? Here in this portion, this is what? Y cap. I told you from here, from this given information. So, so this is the loss function. And this is already defined in equation 5.11. And then equation maybe here, this is averaged form. And here it is single form. Huh? So by using, you can say by using that equation 5.11 and that average form, now we are repeating that equation. Which was that? What was the equation for that loss? It was loss of WB in weights. In weights. So y log sigmoid of W dot x. I am writing that same equation here as it is. As it is. Plus 1 minus y log 1 minus sigmoid W dot x. If I will go back again, if I will show you. So y log sigmoid W dot x plus minus. So I am writing that same equation there again. The cross entropy loss WB. I am writing that. I will use this equation, okay? I will use this equation. That's why. So here the value of theta is updating. After this subtraction, this value from the right-hand side, it will be updated here. That's why we are saying we want to update the value of theta. And this value of theta, we cannot update until we will calculate this loss function. And then what is the equation of that loss function? This is that equation for the loss function. This yellow one, 5.20, this is the equation for that loss function. So we have to calculate this first, and then we will have our value of theta, which we here in this equation, we have to calculate this loss first. When we will calculate, then we can multiply it with eta, and then we will have the value in our theta. So that's why we have to calculate our loss first. That's why this equation is there. And now, if you apply, and what is here, gradient of that loss. I can clear this and then you will understand. So we have the equation for this loss already. We have to calculate gradient of this loss, okay? Which means derivative of this loss. Which means derivative of this loss. We have to calculate. How we can calculate this? There is it. One page or maybe 1.5 pages calculation is given here in this book. I have made the link, okay? If I will click over it, hopefully it will open because this is offline, not online. Okay, this is the book and logistic regression. It will go to page 80. And what is that? Section 5.8, huh? Section 5.8. Where is it? This is section 5.1. So section 5.8. So 5.4. This is what, huh? Here we have that equation, and then what is our equation? This one, y log sigmoid something, and then this, if you will take the derivative, then this equation will be finally summarized, or you will get this as a derivative of that equation, okay? That's why I have given the reference. And in your thesis, when you will do something like that, you have to give the reference, huh? So now here we are going like that, and in this way, what is the final form? This is one form, section 5.8, sigmoid W dot x plus b minus y xj. We will reach there, okay? We are reaching there. You can say sigmoid W dot x plus b minus y multiplied by xj, okay? So we are using this equation. We are using this equation, and I have given the reference here. If you will apply the derivative over this equation, That calculation is mentioned in section 5.8 of that book, which is for the natural language speech and natural language processing. What is that book? I can give you also the name. Okay, what is that one? Yeah, this is speech and language processing, okay, by Daniel Jurafsky. Okay. When you will apply the derivative here, now, then you will get this final answer. From this equation 5.20, you will get this answer. And what it is, partial over partial Wj, loss on these weights, you will have sigmoid of this W dot x plus b minus y xj. If I will explain, I know that this is what, this is my previous z, and this whole sigmoid W dot x is what, this is my y cap. This is what, this is my y cap according to my previous studies. I can show you that slides. You can go back and then you can see that sigmoid W dot x is what, it is y cap, because it will give you the probability value. That would be probability value of your class y. And when you will use the threshold, then you will get y cap. So that is basically y cap on the and here it is basically y cap minus y, and then you are multiplying with the input. And you are multiplying with the input. So when you calculated derivative, when you apply derivative over this, then derivative is giving you this equation, which means when you applied gradient over this loss, then that gradient is giving you this equation. Then that gradient is giving you this equation. Now you can put this equation here. Here, gradient of loss. And now, after applying the gradient over this, you got this equation. Now, putting this result in our equation, then finally we have what? Now, putting this here, or you can summarize it further. So, this is now the gradient for 1 point. This is now the derivative for x only. And if you want to convert it for all the variables, then this is the equation. Again, the same, sigma from 1 to m variables. And sigmoid w, and wherever you have the x, that is representing xi for multiple features. And where you have the y, it is for your multiple class labels that are available in your data set. And you are multiplying again with xj, as you are multiplying here with xj I again. And this is the final equation for calculating the gradient for that loss. Now, we will use this. So this is the equation for calculating the final gradient of the loss. And what is the gradient of our cost function? We said in the beginning. What is the gradient or derivative of our cost function? It will do what? Minimize the cost function. So now this equation that you have here, this will minimize the cost. This will minimize the error. Okay, this will minimize the error. We will use this concept now in algorithm. Now we are going to present the algorithm here, which is the stochastic gradient descent algorithm. And here we are passing the loss function into it. You know what is loss function from the previous slide. And then we are passing some function. You know also f. F is x semicolon theta maybe. And then we are passing x and y. And what are these? L is loss function. F is function which will have the weights into the form of theta, you can say. Theta is what? Representing what? Weights. So this f is what? It is a function, and it will what would be the parameters of this? Theta. X semicolon theta. So input and also the weights, huh? The inputs and the weights. And x is what? X is all training inputs from x1, x2, and xn. and y is what? The training labels in the data set. The same y, that the same concept that you have in the previous slide. So it is y1, y2, yn, which means yi's and xi's. Now the variable theta is 0, and then we are introducing a loop with repeat t times. And here t is what? This is now discussion again. This is now discussion again. You can start with some higher value, and then that value will become 0, then you can terminate, okay? Then you can terminate. Because in the gradient descent algorithm, you want to reach at the global minimum, then okay, you can start with some higher value and then you can terminate it at 0. Anyhow, but it is written repeat t times, so t can be 100, t can be 200, 500, how many, it depends on you. And then here, for each training tuple, we have xi comma yi. We will select input, and the y is also available in the class value from the data set. Okay, I have given you the example already, PyMy Indian data. So you are reading one row and also the value there in the last, for example, class variable. So you can select any tuple from the database randomly. It is mentioned there. You can select randomly. Okay, we can, but randomly you have to do it for all the inputs, for all the xi's, and it will be automatically for all the yi's. And then we are doing what? Then we are calculating here f xi comma theta. This is a function, and this is equal to what? This is equal to what I said in the previous. It is equal to y cap. It is equal to y cap. Y cap is what? It is something, the class which would be predicted by our model. Predicted by our model. So if this would be the class predicted by our model, then it will calculate the probability. Okay. It will calculate y cap is what? How we can get the y cap? It will calculate the probability. It will pass through the sigmoid or something. The first two steps that we have seen in the logistic regression. The complete first two steps. Here that will be, so our model will compute the y cap for this thing, for this input, either it is x1 or whatever, with these weights. Theta is weights, wmb, we already have said in the previous slide.
Values for this.
Whatever, for example, it if it is the PyMy Indian diabetes data set, then the first row, which will have the values, not the column, not column headings. Okay, the first row. Yeah, those values, if there are nominal values, you have to convert those values in numeric form also. Okay, because logistic regression deals the data in numeric form. I think I talked already something maybe in the beginning, or I don't know. So here you have to compute that y cap. So here you have to compute the y cap, and the first two steps that we have seen up to logistic regression, up to here. Okay. Up to here. Here we are calculating probability, and then we are deciding y cap here. Okay. I'm talking about this. So this is that step. Okay. This is that step which is in there in that algorithm. And the previous step, taking inputs, it is also mentioned in that algorithm. So all the four steps would be there in that algorithm. So first step is taking input. Here we are taking tuples, training tuples, taking input. And then here we are computing probability values by using that second step. If we have fourth step, and then here we are computing the loss by using that third step that we discussed mathematically. What is written here? Loss of, I can remove that drawing. So the loss of y cap comma y. We have seen equation for that. We started the discussion. For example, if we will go back here, loss function, we started the discussion from here, and then we reached on some equation for that. This is for the whole training data. Okay. So yeah, so this is for the one instance. So now where is that? So this is what we are computing that loss, the third step. We are computing that loss. Third step, how much difference between the y cap and the y is we are calculating, that we have seen mathematically there. And then here, delta theta loss of f of xi, and this is y cap and then y. This is y cap and this is y and this is gradient. So this is for one observation and this is for all weights. One observation but all weights. You are taking one observation in each iteration. Huh? So now it is confirmation that this is one observation, but now you will take all weights theta. How should we move theta? Here it is minimize loss, okay? Not maximize loss. So here we are basically calculating this part of the equation. Equation 5.9, we want to get our optimized value of theta, and here we will get the optimized value. But first we are calculating this gradient of the loss function. Loss function is the third step where we have the equation. And then we are calculating the gradient for all the vectors, and that is this one, fourth step. And then whatever the value we will get, we are storing in G, and then we are using that equation. What is that equation? This one. In simple form, in general form, theta is equal to theta minus eta multiplied by that G. Yeah. So now it will learn the values and it will update the values here. And now we will take some example and we will execute this algorithm over it. We cannot run all the steps because it is logistic regression, but we will run one or two steps to get the understanding. Here, we are taking the same text which we saw in the previous example. That is the text of some reviews about some movie. And in the previous example, we were having 6 features, huh? But here we are considering only 2 features, okay? The important one. And we are leaving the others, okay? Only for this example. We are considering only 2 features, the x1 and x2. Here x1 is what? 3 positive words. Count of positive words. And x2 is what? Count of negative words. That is 2. That is 2 here and that is 3 here. Now we are, and what are the initial weights? Theta 0, you can say. Theta 0 means the values of theta at the 0th time. Huh? Suppose we have W1, W2, and the bias. Suppose we have this 0. Huh? This is given to you first. And the eta, which is learning rate, it is also given to you. Then how you have to move on? According to that algorithm, how you have to move on. Okay, these are the given values. Then here we are going. This is our equation, theta t plus 1 theta t minus eta gradient loss of y cap. This is I am calling y cap, okay, shortly. I don't want to say it in an f of xi semicolon theta, so that's why I'm saying y cap comma yi. So this is our equation. This is our equation. And according to this question, what are the weights given to us? W1, W2, and B. 3 weights are given to us, huh? 3 weights. If you will exclude biasness, then 2 weights because we have 2 inputs actually, x1 and x2. One W is for x1, W1 is for x1, W2 is for x2. Now, we want to, this is our equation to get the value for the theta. But for that, we have to calculate the gradient. And how we will calculate the gradient? So first you must have to know how many weights you have, how many dimensions. Here we have the word dimension. So how many weights I have? W1, W2, and B3. Then I am going to use this equation, which is 5.8. 5.8. This is closed form. This is open form. This is the open form to find this gradient of this loss. How? Here, this is the equation. I am just repeating that this is the equation. Gradient of these weights. If you want to find the gradient of these weights, the equation would be partial over cross entropy loss of this weight, partial over partial W1, partial over partial W2, and the partial over partial B. Simply. The other things are same at everywhere. Okay. It is easy to memorize. Huh? The only thing difference is I have to calculate the partial derivative for W1, for W2, and for biasness. This is written according to that previous equation that I have showed you here. According to this equation 5.18. Now, this is the partial derivative. And this, how can I write it? If you will go to this previous, this is that equation. Huh? This is for the all, and this is for the single variable. How you can, what is the, how you, the derivative of this loss is what? This is the derivative. We have taken this equation, and then I have given the reference that in section 5.8 of that book, this derivation of that equation is given. So by using that information, we reached on this summarized form, or we reached on the answer of that derivation. So now we want to find, so this is the equation, partial derivative of single input observation, not for all variables. Or if I will talk in terms of weights, then I will say this is the equation for single weight, huh? Not for all variable. Okay, and here what I want to do, here this is the gradient of the weights, and in these gradients we have partial derivative for each weight. Now I can use that equation. That is what? Sigmoid of w dot x plus b minus y multiplied by x something. Here, if you will see, sigmoid of w dot x plus b minus y multiplied by xj. I am using that equation there with respect to w1. I am using that equation there. How can I write this with respect to w1? I can write sigmoid w dot x plus b minus y. Y is the class which is available in the data set. And multiplied by with what? What is its related input? This is the weights, and x1 it's iterated. Multiplied with x1. And here w2, this is the weight w2. So I can replace, I'm writing according to that previous equation. I cannot go back, okay? So sigmoid w dot x plus b minus y multiplied with x2. And here it is only biasness, so you don't have to multiply. It is sigmoid w dot x plus b minus y. So now you have these equations. And these equations are written according to this equation 5.21. I can quote that it is written according to this one, but then it would be for all data points, then maybe it will create confusion for you. So that's why I am using this equation. Anyhow, so now put the values and calculate the values. What value what is the value? What is the value for W1 and what is the value for X1 you have given? Because here you are calculating the derivative for W1. So whatever W you will have here, it means W1. Okay. It means W1. You are calculating the derivative with respect to W1. So you have, wherever you will find W, you will consider it W1. And what is the value that you have for W1 here, W1, W2, bias, all are 0. Initially, all are 0. So then what? 0 will multiply. If it is x1, 0 will multiply, it will become 0. Biasness is also 0. So you have 0 here. Huh? So then I can write sigmoid of 0. Okay? Okay or not? And here again, this W, what value you have for the weights? So this is for W2. So now you have, what is the value for W2? So it is again 0. So 0 multiplied by input is 2 or 3, but leave it, it will become 0. Huh? And then you have the biasness 0, and it is again 0. And similarly here, you have the 0. And this y, what is y here? It is given. I didn't mention, but it is given in the question. Your y is 1. We are considering only two features for which we are saying that our y would be 1. That y which is available in the data set, we are going to consider for that class. Okay, we are going to consider for that class which is available as 1 in that column. Huh? The value would be 1. Huh? So now, so that one is written here. According this y, that one is written here. And now what is the sigmoid of 0? If you will calculate on Google or whatever, it will give you what? 0.5. And normally, if I will show you this sigmoid curve, this is the 0, and here at 0, if you will see, this is 0.5. Okay, it is 0.5. So it will give you what? It will give you the value 0.5. Where it is. So sigmoid of 0 is 0.5. 0.5 minus 1, you will have minus 0.5. Huh? 0.5 minus 1, you will have minus 0.5. And x1 is again multiplying with it as it is. And here you will have the same result also. And here you will have the 0.5. This sigmoid of 0 will give you 0.5. Then after subtraction, you will have minus 0.5. This is for W1. This is for W2. And this is for biasness. These values. Okay. And now when you will multiply this 0.5 with value of x1, x1 is what? 3. So 3 5s are 15, so 1.5 negative. Huh? And what is the value of x2? 2. So 2 5s are 10. And then if you will handle this fraction, it would be 1.0 negative. And this is as it is. So now these are the values for this. And if you will put in the equation, okay, then okay, theta square. Here I'm writing theta square because I am considering these first values that you have here for theta 0. Huh? And then the next here is theta 1, and here you have the theta 2. Values of theta at 0th point, 1th point, and when the time is 1, when the time is 2. Huh? So theta square, and here we have I am writing for understanding only. W1, W2, B, and then minus eta, we are using this equation. And these values that you have calculated, write them here. And what is the value of eta? 0.1, 0.1. So multiply all these values, 0.1 with this minus positive, and then finally it will be 0.15. And 0.1 multiplied with this one, minus positive, and then you will have this one. And also minus positive, then you will have this one. If these weights are 0, okay, we are also considering it 0. Then again, 0 minus this, you will have the same result, okay? You will have the same values. Now, these are the values of the weights W1, W2, and bias for theta 2. For the time 2. Now, the new weights for your theta. The new weights for your theta. And in this way, you will keep on iterating with the loops. Huh? One iteration of the algorithm is finished, okay? One iteration of that algorithm is finished. we have assumed something already because this is something easier. Half of the steps of the algorithm we have assumed. We have given that it is y is equal to 1. These are the features, and these initial weights are this. Half of the values are already done. Eta is given. So this is the probability that this class will be predicted. Huh? So you are giving this direction there. And then you can calculate if your class is already predicted. Okay. If you will keep on going like that, now we got these weights. For example, what these weights are giving us the idea. This is W1, this is W2, this is Bayesian. W1, after the first iteration, W1 has the highest value. W1 has the highest value. W1 is the weight for the X1, huh? And X1 is the feature of what? Positive lexicon, which means now the result are going towards predicting the it is already done. We know that it is positive class, but it means now the weights are moving towards the positive class. So after one step, the weights are shifted from 0 0 towards positive class. Towards what? Positive class. And uh, if you will move on like that with further positive examples, then this weight will be higher. But if our model will observe some negative examples, then this weight will be shifted to this W2, okay? This W2. This is how the weights are being optimized in this stochastic gradient algorithm. This is now the source code for implementing logistic regression. Here, if you will see, I'm just importing some libraries. So matplot, numpy, all, I am loading the data set which has the name load digits. This load digit is available in sklearn library. The name of the data set is load digits. It will have only numeric values. Logistic regression needs numeric values. Okay. So this data set is designed especially for these type of models. So I am loading that. And then from that sklearn library, we are importing logistic regression. It is available there. It is also available in some other, but also available in sklearn. And then, okay, these are general. From sklearn, we are importing classification report to show the report of the classifier in terms of accuracy, precision, something like that. And then we want to show the confusion matrix. We already seen confusion matrix in lecture 1. And similarly, from sklearn library, we are importing this train test split. This module which we will use to split our data set into training data, test data, and something like that. And then from sklearn, we are using this module standard scaler. Through this module, we will scale our data. When we were studying how we can pre-process our data, at that time we have studied some topic scaling of data, or standardization of data, something related to balancing the data. And here, first, in the first step, this is comment, leave it. So this is a comment that we are now going to get the data set here in this statement. Load digits. We are loading the data set into the form of X and Y. Into the form of X and Y. These are the comments, you can leave it. This is the explanation. This is the explanation about this data set, that now when you will load your data set in X and Y, then X will contain what? X will contain 1797 rows and 64 columns. Now this X will load the data. This is the number of rows and the columns with values what? Ranging between 0 and 16. This is the data that you have in X. And what is the data that you have in Y? Y is a one-dimensional array. That would be a class. Huh? it will have 1797 values again, and only with one integer between 0 and 9. Between 0 and 9. So it is the last column which is containing values. So here I am just, this is not the source code, okay? I'm just showing that this is the picture of X and this would be the picture of Y. Okay. So here I have commented this text. Okay. If you will copy paste, it will work. Okay. It will work. This is the source code, but I have commented it. I have pasted the output here just to give you the idea what is that, what is the, yeah, what you have here in this X and Y. The, the font is very much small, huh? Anyhow, now the pen will not work. So you have to go with the cursor. And here I am splitting my data set. Train test split, which we imported. I'm splitting my data set into X and Y. Yeah. This 0.2 means 20, 80%. Okay. With the ratio 20, 80%. So we divided our X into X train and X text, Y train and Y test also. And this module will automatically do all that stuff for you. It will distribute 80% into what? Into X train and Y train, and similarly 20% into what? Into X test and Y test. And in the next step, we are scaling our data. Before applying the logistic regression, we are doing something good with our data. So we are balancing, you can say, our data. We are scaling our data by using that mean zero and standard deviation one. We studied this when we were in our CLO one. We studied this by using this thing. Standard scaler is the module. This is the object we have created. And through this object, we are calling this module fit transform. And we are passing our training data into it. And that will be scaled. That would be scaled. And here we are applying the logistic regression. Solver is equal to liblinear. There are different algorithms, liblinear, LBFG, and some other. These are the algorithms for optimization, huh? For optimization. And you can write this, for example, here. If I will write, yeah. I want to copy it, but it is yeah. If you will write this line, what I want to say, and if you will write it here, and it will directly, now you are going directly to scikit-learn, and you will see what different types of, oh, too much variables. Even I don't know what these variables are doing, huh? So but our related variables are what? For example, this linear first. So what is, and then I will show you. Okay, I will show you. And here linear, LBF, Newton CG. So these are the different algorithms that you can use for optimization. Okay, for optimization of different values. And here we want to optimize, something. But here this will be used for some different purpose, not for optimization of your weights, similarly, what is the other thing? You can understand something like that. What are these values? You can just paste this line there, read that, and then you can understand what it is. So this line is giving you what? Here we are using simply the logistic regression. And here we are simply calling that module. And before that, we have done too much mathematics there, huh? We saw too much mathematics. And here you are only calling that logistic regression. So, but with this line, this model will be created. But now we are fitting our data, X train and Y train into it. We are putting our training data into it so that this model will get the training, huh? And then X test should be scaled as well. So we want to test our test data. So we are going also to scale it. We already scaled our data here. Here scaling means we are fitting our data. Maybe we will have outliers or something. We are removing that, okay? We are removing those higher values and it would be between 0 and 1, maybe something. Maybe, I am not sure. Maybe. I have taught you this topic already, so you can go back and you can see what was that topic. Okay, now I am forgetting that topic. Now it is not my responsibility to memorize that topic always. Okay, you can go back and you can see what is the effect of that mean zero and standard deviation one scaling. Okay, and here the test data that we want, we are also scaling that data by using that same scalar. This is the scalar, is the object for that standard scalar. We are using that scalar dot transform x. We are passing the test data. It will be also scaled like your previous data. And then here, what you are doing, model dot predict x text. You are passing your test data into it, and your model is what? This logistic regression. And you are asking to predict over this test data. What is this? What is the class of this test data? Huh? And it will predict, and this will come here in this y predict. In this y predict. So you have a new variable y predict for that. And then here you are printing the score of that model for this prediction. X train is the training data, y train is the also training data, and it will print the score. I have made it comment, okay? It will not show you anything, but if you want to show something, you can uncomment it, okay? And then it will show, it will give you the score for the training data, okay? The different scores it will give you for the training data. Similarly, for the test data, it will give you different scores into the form of, I will show you. And now here simply we are displaying the confusion matrix. What is confusion matrix? This is called confusion matrix. We already have seen, okay? This purple one is called confusion matrix. So here, uh, confusion matrix, y test, we are passing our uh, test data, which is our gold standard y test, and predicted. Y predict is what? Y predict is the things which are predicted by our model, okay? When we provided the test data, then y predict was what? Here, if you will see, this is the y predict. This is the prediction by the model. This is the prediction by the model. And what is y test? This is the data that we have here. And these two variables we passed here, and then it will print the confusion matrix. And this is the display for that by using matplot library, by setting the confusion matrix, different colors or such, and something like that. You can read it by yourself. And finally, here print, no comment here, print classification report. This is the module I am going to use. This module I called here classification report. So classification report, and we are passing by test and the prediction result. We are passing into it, and it will give us the complete report which you are seeing here. This is the precision. It is calculated for the class 0, for class 1. These are the different classes from 0 to 9. For class 0, what is the precision? What is the recall? What is the F score? What is the support? And similarly for 1, what is the precision? And similarly for class 3, 4, and so on. Then macro average, all that. So all that stuff is calculated through this single command, classification report. Okay. So, okay. If I will run it, it will, I don't know, maybe it will run quickly. Maybe I'm stopping now, huh? So that